Yeah, thank you, Jeff. Ladies and gentlemen, I'm very happy about the workshop today. After establishing the Center for Energy Innovation a couple of years ago, after changing the focus on membrane technology, after Jeff became the director of the center, and after moving to this new building with excellent lab facilities. So the message is for today, we are ready now, and we are hungry to show you the performance of our membranes. We want to test our membranes for your application. We want to modify and to optimize our membranes to meet the requirements of your application. And after successful testing here in the CEI labs, we want to go to your site to run pilot tests and to convince you that the membrane is the right choice for your separation purpose. Well, I would like to talk about ceramic membranes. It is not surprising because you know that we are a ceramic institute. Ceramics have a very good stability. They are very robust. You know that for sure, but you need a membrane with the right selectivity and a high permeance. And this is what we are working on. We are developing inorganic membranes on top of porous ceramic substrates. But we are Fraunhofer. We do not stay with the membrane research. We want to bring the membrane in application. And that's why we have in our labs possibilities to start from the substrate. We adapt the substrate to the requirements of the membrane. We do a lot of membrane research. We put the membrane in the module. We design new modules. We run process engineering. We are able to build small and medium-sized plants ourselves. And we assist our partners and customers in application. What does it mean? We run pilot tests, we go on the site, we implement our membranes in the plant, and we assist you over a longer period. So it's normal that during a regular inspection, we replace single membrane elements when we test the performance in our lab again. And so we learn a lot about long-term stability of our membranes. This is important because if you want to bring new membranes in application, you have to know more about stability, reliability. This is one of the first, or maybe the second question. First question is how much costs the membrane. Second question is how is the lifetime and long-term stability of the membrane. Well, in the field of membrane development, we have different materials. We have in total about 50 people working on membrane development and membrane technology. One group is working on oxide membranes, titania, zirconia, alumina, as well as silica membranes. The second group is working on carbon materials, microporous carbon, carbon nanotubes, graphene. And in this group, we also perform development of non-oxide ceramics because it is a similar preparation technique. So we are working on silicon carbide, silicon carbon nitride. The next group is working on zeolite membranes. You know that zeolites have a specific crystallographic cage, and we prepare thin zeolite layers on porous substrates without intercrystalline pores. So we use only the crystallographic pores for separation. We are working on mixed ion electron conducting membranes. This black material here is a perovskite material, which is can be used for oxygen separation or other materials for hydrogen separation. And we are working on palladium and palladium alloys for hydrogen separation. Well, today I don't want to talk so much on membrane preparation. I would like to show you a couple of examples of successful projects where we applied our membranes, and hopefully you understand the way we are working. Well, the first topic is liquid filtration, mainly water treatment. And here, this is, of course, well-known. Ceramic membranes are well established, especially in microfiltration and ultrafiltration. Together with our strategic partner, Rauschert, we succeeded in the development of nanofiltration membranes, and today we are the only group worldwide which is able to prepare and to produce ceramic nanofiltration membranes. And in particular, we developed two different types of ceramic nanofiltration membrane. The first one with a molecular weight cutoff of 450 Dalton, the second one with a molecular weight cutoff of 200 Dalton. Water flux is in the range of 20 liter per square meter hour and bar, as well as 9 liter per square meter hour and bar. The membrane itself is a very thin layer of titania with a small portion of zirconia on top of a mesoporous zirconia and titania interlayer. And you can imagine that to prepare these thin membranes in hundreds of square meters, you have to run the preparation under very controlled conditions. We perform this coating here in the clean room to avoid any dust during coating and to control the humidity, because during preparation the membrane is sensitive to humidity. After heat treatment, after sintering of the membrane, it is very stable. You see this, the chemical stability in an acidic and alkaline solution. And this membrane was optimized for this 19-channel tube and is already in application, in operation in about 50 different applications. And these applications were mainly in process separation. Thank you, Manny, for this term. We call it production integrated separation. So we go inside the industrial processes, we clean only a partial wastewater stream, we recycle the wastewater, the permeate, and on this way it is often possible to not only to recycle water, but to recycle a lot of heat as well, and so you get a very short amortization time. For this development, we got the Corporate Environmental Achievement Award of the American Ceramic Society 4 years ago, together with Rauschert. This was an award ceremony in Ohio, Columbus, Ohio, and I remember very well this. We were and we are very proud of this, about this award. Well. With applying this nanofiltration membrane, a lot of, or a couple of applications, of large-scale applications came up, where the first of my already mentioned two important questions was difficult to answer. How much costs the membrane? If you need a large membrane area, it is difficult to convince the people for application to use ceramic nanofiltration membranes. And that's why we are working on the scale-up of the membranes. We already succeeded with a 1.3 square meter membrane element with 159 channels, and with a 4.5 square meter element with 559 channels. We want to continue it to achieve a 10 square meter element. And this way we will be able to cut the costs by about 50%. Well, and with these upscaled membranes, we will be able to go in large-scale applications, and this is one which already Alex mentioned in his talk this morning, the treatment of wastewater from tailing ponds in the oil sand mining. This is a pre-treatment before reverse osmosis, and because of the oil and bitumen content and abrasion particles in the wastewater, it's not possible to run this pre-treatment with a polymer membrane. And after a first step of testing with a small unit and demonstrations that the membrane is feasible in general for this application, we implemented here together with Rauscher, together with the company Junghans, a 235 square meter plant in Alberta, Canada. And this is already running now for more than 2.5 years, very successfully. And hopefully the companies in Canada will decide quite soon to invest in a full-scale plant, which will be about 10 times bigger than this pilot here. Well, next application is in gas separation, evaporation. You know that in chemical process engineering, separation is the main part and the most expensive part of the process. And here's a big potential to reduce costs, to increase efficiency by applying ceramic membranes. The first membrane we developed for these applications is a zeolite membrane. In particular, it is a zeolite A membrane. And this membrane was tested for the dehydration of 3-ethylene glycol. First in our lab, 3-ethylene glycol is an absorbance for the drying of natural gas and is normally dehydrated by a distillation above 200 degrees C. And this high temperature distillation can be replaced by the application of our zeolite membrane. And again, after demonstration of the feasibility in our lab, we implemented 20 square meter of these membranes in the pilot plant, which is able to try 10,000 cubic meter of natural gas. And this is running now for 1.5 years. And again, here we hope that Energy and VNG decide to build a large-scale plant in the near future. Well, next example is also with the zeolite A membrane. It is evaporation or vapor permeation in this particular case with zeolite A membranes to the dehydration of bioethanol. So the membrane, this is well known, has a very good performance. If you start with 10% water in ethanol at 120 degrees C, you get a flux of nearly 12 kilograms per square meter an hour. And a very huge selectivity of 2,000, 3,000. Here we are able to test membranes for dehydration of solvents in our lab, also in large scale. And in this particular case, for the dehydration of bioethanol, we implemented membranes in the first pilot already in 2007, then in the first demonstration unit in 2009. Then it was increased to in capacity to 170 square meters. And in the meantime, further plants with our membranes are in operation in Ukraine, in China, in Paraguay. So, and here again, we assist the people in the application. So that means our staff is going to China, to Paraguay. We go on the site, we replace membranes, we give advice in using our membranes. Well, next example is gas separation with carbon membranes. This was a project together with BASF. Here we showed the single gas permeance of the carbon membranes. We found that we have a very good permeance for hydrogen, and the hydrocarbons C3, C4 are completely rejected. This was the basis for mixed gas measurements and tests together with BASF. And you see that the high hydrogen permeance, high perm selectivity was confirmed also in mixed gas separation. And this confirms that we have here a molecular sieve behavior and a very stable performance of the membrane. Well, next example is in oxygen separation with the mixed ion electron conducting membranes. Here we succeeded in the development of high performance membranes, perovskite membranes with very high oxygen flux, and then we focused on on the energy consumption, on efficiency of the membrane process. And you see here that we were able to reduce the energy consumption per cubic meter of oxygen, and with 0.7 kilowatt hour per cubic meter, we are close to the efficiency of a large conventional air separation unit. With the advantage, this is a modular membrane plant. You can switch it on and off. You can adapt it to the size of oxygen you need, and it's much more cheaper than to buy oxygen and to get oxygen delivered as liquid oxygen in a tank. Well, interesting application of our membrane is very close to separation. So we are developing membrane reactors. There is a big potential of application in this field. We are just now focusing here on the reaction of hydrogen and CO2 to form methane or methanol, and we are working on the preparation of syngas from methane. We heard already in the presentation from Praxair that this is an interesting approach to use oxygen separation membranes. And in the further transformation of the syngas to synthetic fuels, hydrogen is formed as well as in these previous two reactions. And so we have a limit in the equilibrium of the reaction. And our approach is to remove the water from the reaction and to shift the equilibrium to a higher yield. At the same time, the methane, you keep methane on the high temperature feed side, and you can feed it to the natural gas grid. So it's very challenging and difficult because it's difficult to bring the kinetics and thermodynamics of separation and reaction on the same level, that you can really combine it, that you can prepare the catalyst coating directly on the membrane. But we are working on that, and here you see an example of such a reactor. So we have also people in our lab experienced in catalysis, in process engineering, and you see here this is a reactor for the CO2 hydrogen reaction to methane or methanol. Yeah, at the end of my talk, I would like to summarize more or less our offer. What we are offering as Fraunhofer IKTS. We are offering membrane development. We are offering membrane preparation and membrane supply for piloting, for demonstration. We are offering membrane testing. Membrane testing means we test our membranes for your application, and we are offering technology transfer. All these things you can contract with CEI, and if one of these points cannot be performed by the group here at UConn and CEI, then CEI will subcontract it to IKTS. And from this cooperation here with UConn, and this is my last slide, we have a benefit for both sides. So Jeff already mentioned it in his initial talk today. He's a polymer membrane guy. We are we are specialized in inorganic membranes. We learn from each other, and we want to develop new things, new membranes, new membrane processes by combination of polymer membranes and inorganic membranes. This is a topic we want to perform here in CEI lab. This is a picture of the booth of CEI during the conference of International Conference on Inorganic Membranes, which we organized 2018, one year ago in Dresden. So with this slide, I would like to end my presentation. Thank you very much.
You know we have a close partnership when they get me to come to an inorganic conference on inorganic membrane conference. Are there any questions from anyone?
Can you make some further comments on the relationship between Fraunhofer CEI and IKTS in Germany? So if you subcontract through Fraunhofer USA, and is there any issues with working with United States organizations and even trying to develop some mechanisms for co-funding or something in Europe, right? I mean, does Fraunhofer look for cost share? Does it look for 100% financing of any project? If you could just talk a little more around the ways of funding, particularly outside of 100% paid, and the any issues with respect to where the work is taking place.
Yeah, first of all, CEI is a joint action of UConn and Fraunhofer IKTS, and it is under the umbrella of Fraunhofer US. Our intention from IKTS is to be able or to make it easier to cooperate with US companies on membrane technology on separation, because it's very difficult to do it overseas with Germany directly. That's why we supported CEI here in building up the right equipment, and we have people from our lab here as visiting scientists. They work on the installations, and they use our membranes, and so you will be able to test our membranes here in the lab, and you can contract this with CEI directly. But so far we do not perform membrane preparation here in the US and membrane development. This would be a completely other story, and this is what we are doing in Germany. And if there is an interest in this membrane preparation, membrane technology, then we can cooperate with you, with Fraunhofer IKTS, with you directly. Or if there are some problems, if it is too difficult, we can do it via CEI. It's no problem.
Any other questions? One quick one.
On your example, you're showing that you can go to a maximum capacity of 1,000 square meters. So how the business model works? So Fraunhofer can provide membrane to do all the pilot testing, assuming that it's successful. Let's say that we need significantly higher amount of membrane. So how the model work? Are you partnered with a particular company, or if we want to go over the 1,000 square meter limit, how that would work?
First, we are happy that we have built up the capacity or the production capacity to be able to prepare new membranes immediately after the development in such a scale, to be able to provide it for pilot installations. But of course, if you need membrane for large-scale applications, then we need a producer of the membranes. And we have a network of partners. I already mentioned Rauschott in the field of nanofiltration membranes. And we are open to cooperate with membrane producers in the other fields of membranes for gas separation, perforation, vapor permeation. So we are very open for cooperation in this field, and often it is helpful also for these companies that we have a capacity to prepare first membranes after a development phase before building up an own fabrication capacity. And so it is a win-win situation anyway.